So let's start, since we can't get behind today. Introduction to fluorescence we just did. Two-level model, linear, weak excitation limit, saturated, some differences between atoms and molecules, fluorescence spectrum, excitation spectrum. So if the flow is steady, if the flame is steady, so we did some work at high pressure flames at about 50 atmospheres, steady, just sitting there. We wanted to measure NO, or we wanted to develop techniques for imaging NO. So we would, we had the knowledge of the NO spectrum. We would pick a wavelength we wanted to excite. We had line-shaped models, so we kind of knew what we were exciting. We could then scan our spectrometer and see what the fluorescence spectrum was. Or we could collect a broad spectral region, broad collection, and scan our laser. Usually that's what you do. So we decide where to set our collection bandwidth to avoid flame emission. We would scan our laser slowly, and then as we're scanning a laser, we're taking signal versus wavelength. Roughly, this looks like the absorption spectrum. Roughly, it's just the absorption spectrum. And you can learn about line broadening and how to go about things. So when the flame is steady, you can do some things to kind of figure out where should you park your laser so that when you take a PLIF image, it can be quantitative in terms of something. So, and that's when we found out that we had trouble with interference from CO2 emission and fluorescence and so on. So if you have a steady experiment, you frequently will scan your laser and collect broadband and see what you see and see if it makes sense, and it's roughly the absorption spectrum. In the limit that the fluorescence quantum yield is the constant, it's just the absorption spectrum. Or you can fix the laser and then look at things as a function of time, but at high pressures, things are, it's done in a short time. So anyway, it depends on the situation what exactly you do, but you use different strategies to find out if everything's working right. Okay, we're going to begin to talk now about PLIF, and we've done a lot of different work. I told you about the infrared. We've looked at hypersonic flows. I've already changed these notes today, so this version is not what will ultimately be on the website in about a month. So we'll proceed through this. PLIF is a two-dimensional form of LIF. There's the 1D, there's the 2D. So the only difference now is instead of focusing the light into a narrow waist, we form it into a sheet. And we actually, you expand it in one direction and you compress it in the other. So at the point that it goes through this flow, it's usually a narrow, thin sheet, maybe half a millimeter in width and maybe a centimeter high or 5 centimeters high. So it's like it's like a sheet. It can be a thick sheet. And so then the rest of it now, instead of collecting onto maybe a photomultiplier, we collect onto a CCD array of some kind. In this case, it was the infrared camera, but it could have been any kind of a camera. And we would see some sort of a flame structure, flow structure. So if you want to do time-resolved imaging, you need intense single-shot lasers. You want this to be a short enough time that it freezes the flow field. It's not the pulse length of the laser. It's the sum of the pulse length of the laser and the time it takes the fluorescent signal to decay. It might be 200 nanoseconds. What determines it? A and Q determine it. So the laser pulse at 10 nanoseconds is usually short. Now the question is, how long does it take for the fluorescent signal to go away? And it depends on A and Q, but it might be a couple hundred nanoseconds. Then if you wanted to have another pulse, you could. So your image is kind of blurred over maybe 100 nanoseconds or so. Usually, in most cases, this freezes the flow field, except for some really high hypersonic cases. Now, because we're spreading the beam out, and maybe, let's say we're looking at a camera that has 100 pixels by 100 pixels. We're taking that beam and we're spreading it out over 100 rows. So we've taken our laser energy and we've divided it by 100. If 256 by 256 array, we divide by 256. So all of a sudden you started having less photons illuminating your measurement volume. So that's an issue. So you might get lower signal noise ratios. You might be interested in averaging, maybe not. You can do the CW or pulse, but if it's CW, then the time scale of change has to be, you have to look long enough to get enough photons, and maybe that's not fast enough. So the general setup is like this. Now, once you've done 2D, it's pretty easy to do 3D. We've done this sometimes, several times. So you put in some sort of a mirror here, which just translates that beam back and forth across your flow field. And you can do that at a pretty high speed. So what determines the observation rate is set mostly by the repetition rate of the laser. Is it a 10 hertz laser? 1 kilohertz laser? The time between the images then is really usually set by the laser. The cameras are usually plenty fast. You can have a camera that goes to 10, 20, 50 kilohertz, kiloframes per second. So typically use some sort of a spinning mirror or something here, and you can then just move this plane back and forth across your image. So you can do 3D or 4D by an extension of 2D. Once you have this cube of data, we call it a cube of data. Once you have a cube of data, now you have to decide a little bit how you're going to display this data. So we got interested for some years in, well, you've got a cube of data, you store it in a computer, you can ask the computer to give you the view in any direction, and so you can play it back a lot of different ways. Called a cube display. You can look on surfaces, look inside. Once you have this cube of data, you can play movies. All right, so one of the things we're often interested in is the species density. Maybe you'd like to know the mole fraction of OH. So you're going to measure the number density in a given quantum state, and then if you know the temperature, you're done, you're home free. Usually we know the A's and the B's and the volume and this, and if we don't know them, we typically can measure them. And one thing you do is you use something like Rayleigh scattering, where the cross-section is known. So you take some sort of known sample, illuminate it, and collect the light. Let's say we could, in fact, commonly what we do is it's a static system. We'll fill it up with, say, acetone. We'll illuminate a pulse of light, and we'll collect the signal. The flow is uniform, so what we're seeing is a combination of the laser intensity distribution and the collection optics. So you're kind of capturing one image. How different from uniform is it? And so you capture in one image the intensity distribution, the collection efficiency, you collect all this stuff and you have it. You can get it in a relative sense if you do that fluorescence with, say, acetone, but if you want to make it absolute, you could use something where the cross-section is known. So you typically use Rayleigh scattering. So there's a way to get the volume that you're imaging, the collection angle, and the camera efficiency. There's a way to get all of that pretty quantitatively. So for the most part, the hardest problem is the Q problem. Actually, it's the F of J over Q problem. What is the Boltzmann fraction? You're going to measure a signal, and you measure the pulse energy. You measure the signal, and you kind of can relate that back to the number density in the state. But you need to know the Boltzmann fraction to get to the species density, and I still need to know Q. Those are the problems that we have left. So there's some tricks. So the signal is proportional to this number density, total number density of the species, times the fraction in state V and J, divided by this collision rate QE, which can be thought of as a number density cross-section C bar. So when you look right at that way, the signal is proportional to the mole fraction of the species. This is Ni over N. Mole fraction of the species times F Boltzmann fraction of T over root T. So if you have seeded the flow with a fixed mole fraction, you can use this to determine T. Or if you pick a Boltzmann fraction that scales as the square root of T, then your image is directly proportional to the mole fraction. There's like two clever strategies. So those are tricks that you can use. They're not perfect tricks, but they're pretty good tricks. So there's always this combined influence of Boltzmann fraction and temperature and quench rate. So it's the flow field where the temperature, pressure, and species are varying, the quench rate is varying. It's a little tricky, but you can get close. You can get close by picking quantum states that are either sensitive to or insensitive to temperature in this way. So let's see, we have some people here from Georgia Tech. So one of my students, Jerry Seisman, we used this trick in the early days of PLIF. We called it the single line method. So we seeded a combustion flow with a fixed mole fraction, meaning therefore that our signal had this temperature dependence in it. So you can pick a quantum state that's intentionally temperature sensitive, and you take an image that is essentially proportional to temperature. And if you know the answer anywhere, you now have temperature everywhere. That worked really well. Single shot means one laser, one camera, one pulse, but you had to seed the flow with something that's not reactive. We used NO, he used NO. That worked pretty good. That was about 1985, 86 maybe. Second strategy that's more common is that you excite two transitions and you take the ratio of the signals and you get back to the Boltzmann distribution. And you argue that the quench rate is the same. So you have two transitions for the same species. Maybe it's nitric oxide, maybe it's OH. But you argue that, assuming you know the laser energies and the collection angles and so on, that the signal is just related to the ratio of these quantities here, the number density, the Boltzmann fraction, and Q. So in the limit that the Q's cancel, then you're really just looking at the ratio of the Boltzmann fractions, and that's a function of T. So that's another trick. It's not perfect, but it works pretty good. Hardest part there is you have two laser pulses, and are they the same from pulse to pulse? You have to usually measure that. So there's always some problem. Now, so I'm going to give you just an overview of how things have progressed over this length of time. I told you that we did this in 1981 or 1982. It was featured on the cover of Science once in about 1983 or so. We got interested in cube displays around 87 it says. I saw a movie by my fluid mechanics friends, and they were showing movies of flow mixing or something, and I thought we have to do something that's that simple for them, that they will see this and they'll like what we're doing. So I put a student on trying to find some tracers, and we had been using something called, well, Mike Pilling called it diacetyl. I've always called it biacetyl, but it's basically the stuff that they used to put in popcorn in the theater. It's like a sticky liquid stuff. It smells. So we were doing that to do this display right here. We excited this with a xenon fluoride laser at 352 nanometers. Simple, cheap camera, just bang, 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 bang. Steady flow. It was a repetitive pulse flow. And so we got cube displays of this pulse flow because the flow was repetitive. It was great. But unfortunately, we had a leak one day, and the people next door smelled it and thought they were getting cancer. So they shut us down. And that was good news, because I then took my next student and says, find me a new tracer, and he discovered acetone, which is now used around the world, because it has some desirable properties, and you'll see what those are pretty soon here. We got interested in scramjets here around in the 90s. That was the very first instantaneous, but two laser, two camera temperature image in a scramjet flow. That was around 1980 something. And one student got interested in actually imaging velocity. There's strategies for that, so that we did a lot of things that appeared in applied optics in those days. I would say that what happened then began, for the last 10, 12, 15 years, you're beginning to see this now transition to other universities, other laboratories. It's practical now, especially the tracer-based stuff. It's really user-friendly. But it's expensive. You still have to have a pulse laser and intensified cameras. The real trend right now, and we're not doing much of this, but is to use high repetition rate lasers. So you do this instead of at 10 hertz, you do it at 5 kilohertz. What does that mean? That means you have to buy a very expensive laser in order to get enough energy per pulse that you still get. You'd like to still have 2 millijoules. You're probably happy now to have 0.3 millijoules. So all of a sudden you're going to see movies, but they're not going to look really, really good because you just don't have enough. So these lasers are powerful. They're inexpensive. But that's where people are today. Cameras are now kind of straightforward. $100,000, $150,000, you buy a really 50 kilohertz intensified, really, really good. Cameras are great, computers are great, lasers are still kind of a problem, but they're moving. And that shouldn't say now the fundamentals of tracer-based PLIF. I fixed that. This was because I knew I'd have some students here from Georgia Tech. This is from Jerry Seitzman, who's a professor at Georgia Tech. We did this, I think it's about 24 years ago, maybe. This was his. In those days, you didn't have the fancy, quick capability to make figures. So this was the figure quality that you had in that period, which is about 24 years ago. But the idea is the same. Here's our xenon chloride. That's an excimer laser. Looks like it's oh yeah, Jerry was good. He figured out a way to do double pulse imaging. I don't think I'm going to show you, but he taught our dye lasers to take two successive pulses and get two bursts of light out of our laser. So I'm not going to tell you about that. So he did so, but he and his partner Bill Paul took these images of turbulent flames, and even today they're not much better than this. This is pretty good. This is a Reynolds number of the turbulent hydrogen diffusion flame, 2 millimeter diameter jet. As a function of Reynolds number, you're going to see the lift-off, the change in the structure. So these are instantaneous OH images. Instantaneous images of something proportional to the OH mole fraction, roughly. Pretty amazing. So now if he would take some cuts across here, and you see this amazing structure. I don't think anybody can calculate this, even now. Those are really impressive. So when you see that, you get excited about what's the potential of PLIF to study flow structures. This is a gaseous flame. There's not that much OH in there. It's really pretty powerful. So that was Jerry Seitzman. But then I've had several good students, but I had another one who was especially good, Brian Kirby. Let's see if I can do this as a little movie. Let's see if this works. I don't know if it's going to work or not. Unfortunately, it may not work. Is it working? Oh, it's not working. It was working. Okay. Now I got to try it again, maybe. It's not working on my screen. Let's go back here. It was working there. Okay. It just doesn't work on my screen. Okay. So, infrared. I don't think anybody ever has done this besides Brian. And I had another good student, Dave Rothermer, who's a professor at Wisconsin. He did something almost as good. So, forced CO2 jet. This is the jet of coming out of a tube. And so what you're seeing is something proportional to the mole fraction of CO2. It's isothermal, isobaric. That's good. But pretty amazing. This is CO2. It's pretty hard to do PLIF on CO2. So this, by using infrared camera, infrared laser, understanding the quenching rate. So there's the potential to use this to do infrared active species that are not accessible by conventional UV-based PLIF. So how do we think about the quenching rate? The quantum yield is the ratio of A over the sum of the processes that remove from observation. So what's Q? It's not electronic. So now you have to think about physical chemistry a little bit. You have to say, well, oh, and this was another here's CO2 and here's some energy levels. You know from CO2 we've got 4 vibrational modes. 2 of them are degenerate. I got the symmetric stretch, the asymmetric stretch, and the bending. CO, fundamental. It's just simple. There's one mode. Here's nitrogen, inactive. Here's their quantum level. This is 1 quantum, 2 quantum, 1 quantum, 2 quantum. And here's the 1 quantum of the asymmetric stretch, 2 quantum. So this was really clever. We excited at 2.3 microns, which excited this transition. So it's the first overtone, but he sent in a lot of photons with a parametric oscillator. Excite this. Now what happens? It wants to instantly become Boltzmannized. So it then excites, it transfers to here. And then because of resonance transfer, it goes over to here, and we get emission from CO2. We don't get any emission from here because it's dark. So we found that if we excite CO, we could get emission at 4.3 or we can also get emission at 4.7. This process is very fast. So you don't want to send in 4.7 because then that contaminates all of your experiment. So this was a clever trick to excite CO, and then you can look at CO and CO2, and you can only see signal from CO2 if there's been a collision that transferred energy, like a way of looking at molecular mixing. This was really a nice experiment. So what's the relevant rate here? We excite here, and so you have to decide what's Q. Now it has to do with, well, where am I collecting light? Am I collecting light from here? Then how do I lose light? I can lose it by VT transfer. I can lose it by VE transfer. I can lose it. So you have to always think about where are the molecules going. And you can then use it to advantage. Maybe you can study the rate of that process. So this infrared PLIF was really great. So then somebody gave us a free CO2 laser. IBM. Nothing's really ever free though. It took us a while to get this working. This is the energy level structure of CO2 that we talked about a little bit. So these are the different modes. So these columns represent different modes of vibration and the rotational envelopes. A CO2 laser actually worked kind of like right in here. By magic, you get a population inversion and you get too many molecules here and they emit back to here, and that's where the laser light comes out. That means that if I buy a laser that has this frequency, or take the free laser from IBM, and if I have molecules with some population here, I can transfer them to here and I can look at their emission at 4.3. So we did this experiment. It's not showing here. I think it's probably 425 Kelvin or something like that. Anyway, just a little heated something or other with some CO2 in it. We just took a picture. So if you knew that the mole fraction of CO2 is approximately constant, this is a picture of temperature. It's a picture of the Boltzmann fraction in this state. So you always can use this to either measure a mole fraction or to measure a temperature. You have to be clever. But I think the trouble is when you go into a flame, you get all this luminosity from the flame, and that turns out to be a problem. But we did an experiment to show how good this could be. We took a pulse of this. Now we had to resort to high power. We got this expensive, free but expensive laser from IBM, 3 joules, which was not exactly tunable. But we sent it through this flame, this diffusion flame structure here, a methane flame. Looks kind of steady. It just kind of sits there. Looks like this. And we said, we're going to measure CO2. So this was what happens when he took a single shot image of the CO2. You only get signal where there's CO2. Exactly how to quantify it is another thing. But this is a picture of CO2. This is what happens when he averages 36 shots. This is what happens if you compare it with a computation that was done at Yale. This is what happens if you use Raman scattering and you take 5,000 shots per row over 500 rows, or about 100 rows. 5 million shots, I think it was, or something like that. No, maybe it was 50,000. So the point is, fluorescence is strong relative to Raman. Then he wanted to graduate and go, unfortunately. And the next student I tried on that couldn't get the laser to work, so we had to, I terminated the project. But okay, I'm going to switch now to some examples. So this is a sequence of examples, and these slides got some errors in there that will get fixed in a month. There's a lot of need to study, opportunities and needs to study complicated hypersonic high enthalpy flow fields, such as the scramjet combustor. How do you do PLIF in flight? I don't think you can, not yet anyway. So you have to figure out a way to study this on the ground. How can you do this? You have to use some sort of you have to work for NASA where they have enough money that they can build some electrically heated thing that runs, or you have to be clever, and so we try the clever route. We use what's called an expansion tube. So an expansion tube is a shock tube with one more section on it. It's a long tube, 100 diameters long, and a dump tank and observation station. At the end of the shock tube, instead of there being a flat wall, it's open and the gas comes out. And it flows over some kind of a model. So there's the driver's section and the test section, but instead of having an end wall here, this section is filled with low pressure helium. And when this pressure shock wave comes down through here, hits this diaphragm, it now sees a low pressure gas. Gas has to expand and it goes fast and it cools down. And the gas that comes out here is going fast and is cold, and you can simulate high altitude flight of, say, any speed you want, really. We would typically do maybe Mach 5, 6, 7, 8, 9, 10. So you can create on the ground for a short time high-speed flow simulating flight. And so we did this some years ago. We did it and we got some really nice results. This was the generic problem. This is called the generic scramjet problem. So you have a flat plate, you have a jet of fuel, say hydrogen, and you have a high-speed flow coming across, supersonic flow, and if it's hot enough, you'll get some ignition somewhere in here, and you get burning for this hydrogen jet. You'll also see, if you look closely, this Mach jet, because this is an underexpanded jet of hydrogen. You'll see boundary layer here, you'll see a recirculation zone in here and here, see some sort of a bow shock, and then you'll see some mixing going on here at the interface between the oncoming air and the burning fuel. So you can do this in a laboratory and study questions about what's the jet penetration and how does that vary with what's called the jet momentum ratio. And the student did this. Now in those days we had, it's probably 15 years ago. Let's see if I can get this to work. This was a very good female student. Okay, good. We had a camera that cost $275,000, but in those days, all you could get would be a camera that would take 8 pictures. So we had to kind of repeat this. This was a real experiment. This was the mixing that takes place for a 2.4 kilometer per second flow at 1300 Kelvin over this jet. And this is your Schlieren picture. So in the textbook, you would have seen a nice smooth bow shock. But now when you take movies, you say, oh, this isn't smooth. It's got some undulations and oscillations. So we learned a lot about this flow field from this camera, even though we could only take 8 frames at that millisecond. I think it was faster than that. I think it was, yeah, this was 10 microsecond, we could run it at different speeds. These were 10 microsecond exposures lasting about 8 milliseconds. Here's the instantaneous one, so the average looks like a textbook. Here's your separation region here. Average looks like a textbook, but the real ones don't look like that at all. That was kind of neat. So then I had another project, which was, so that student graduated. We gave those results to the Air Force. They said, we aren't interested in scramjets right now. So I had to get a project from the Army. And then we had to scrap the facility. Then the Air Force came back a few years later and said, we want you to build an expansion tube. So then we got to build a good one, the one we have now. And now I guess Michigan's going to build one. There's also one at University of Illinois, I believe. I think there's only 3 of them. Maybe one at the Air Force Academy. It's a poor man's wind tunnel. The virtue is that you can get high-speed flows. The downside is that the flows may only last milliseconds. And they're not really perfect. You have to really be careful. There are some non-idealities. But anyway, this is kind of how it works. There's the driver section, the buffer section, and then some expansion section. Now, on my Army project, they were interested in something called a ram accelerator, where you would fill a barrel with combustible gas, and you send in a shaped bullet, and arrange for the combustion to take place at the base and accelerate the bullet, and try to shoot things maybe for the ships or for the Army at up to 3 kilometers a second. And they were building these big tubes and shooting these projectiles and trying to measure things with pressure gauges. And so they would take a big, huge thing and shoot the bullet. You needed a light gas gun. I suggested that maybe we should fix the projectile and flow the gas. That was a really good idea. So we fixed this projectile and we flow the gas over it using our expansion tubes. We put our projectile right there. And so now you have to make sure this tunnel is working. So we would use, say, a blunted cylinder, and we take some images of, this was a 2.2 kilometer per second, Mach 7. So you have to figure out what is the Mach number you're getting. And we did this with NO. So these were pictures basically of NO in the quantum state. So, but you see in the standoff distance, if you know gas dynamics, the standoff distance gives you the Mach number. Or you can take the flow over a wedge, and we do this in my lab class every year. The flow over a wedge of a given angle, the separation angle then tells you the Mach number. If you know gamma, so this is how you check out your tunnel and make sure that it's behaving the way you want. Then you're ready to look at the projectile problem. Actually, we did a spherical nose cylinder. Now this is the Schlieren, and this is the OH. So it's burning now. And we do this with different fuel and oxidizer mixtures. This looks like steady combustion. And then if you push it hard enough, you get this. So what's happening? We got into a regime where this is detonating, and that velocity was high enough for it to actually move forward into the supersonic stream and perturb this. That was the most interesting case of all. So when the free stream velocity coming in is less than the CJ speed, you can get into these regimes. And this was, people tried to calculate this. This is a really tough problem. A lady friend in Japan could do this for, in those days she could do it. She could probably do it faster now. So the idea is to create flows for evaluation of CFD simulations. Back to my female student, she got these spectacular results corresponding to flight Mach numbers of 10 and 13. In this case, we had oxygen, 3.2 kilometers per second. These are pictures of OH. Look at the structure, and here's our hydrogen jet. Spectacular. And people are now still doing some similar work, but it's like 10, 15 years later. Well, that's the power of PLIF, I think. So now more recently, we had a postdoc, Mirko Gamba, now professor at Michigan. He came back and did some of the same things, a little bit different, a little bit better. He took some plan views. So now here's the floor plate, and the jet's going to come through there. And now these are images in the horizontal plane parallel to the surfaces taken at different jet heights. These always blow me away. This is what he sees in the plane, a half of a jet diameter above the surface. Look at the structure. It's unbelievable that what you can see from these pictures. And this is his movie. I always have trouble when I visualize this. This is the floor. Here's the jet. And this is the sidewall. This is a cross plane. So you have to look at this to kind of get oriented. And I think the movie will play by itself. So this is Mirko Gamba, who did this with. He did some of it with a student named Will Helsley, and then some with a student named Vic Miller, who's still with me. So, but now, how did he get these movies? We had to repeat the experiment and take another image. So, because we didn't have kilohertz, we now have. In fact, right now we're setting up a kilohertz system. So we'll repeat this with the. Okay, then I want to now. Temperature is so important. I'm going to show you what we did with temperature. I had this was the way it was around 1995. 2 excimer pump dye lasers tuned to 2 different lines of NO or OH. You're going to take 2 successive images on. In those days, we had to have 2 cameras. Each one had to be monitored, and then we used our shock tube to generate the flow. And this is flow over a backward-facing step. So the flow is coming this way. Here's the jet of hydrogen, and it's going this way. And here's his pictures. So he did experiments in which he put NO in the fuel. So it flows from left to right. And these are plots of the single-shot temperature. So blue is cold, yellow is hot. Flows from left to right. You can see, here's the jet. You can see this recirculation zone downstream of the step that's right there. And you can see that wherever, this is the temperature of the fuel. It's the temperature of the fuel. And you see that it's hottest down here when it goes into near the wall. Then if you seed the free stream, you can get temperature everywhere. And if you look, you can see the bow shock. You can see you can see this expansion right here. So those were true single shot, meaning they were 2 images taken about 200 nanoseconds apart and processed. So an instantaneous shot of temperature. I believe those were the very first single shot temperature images taken with 2 cameras and 2 lasers. It's a very expensive experiment and really hard to do. He then took his 2 colors and he arranged them so that he could look at NO and OH, or he can and combine them. So here's this jet. He's only measuring now where the fuel is. He's seeding the fuel. Seeding the fuel. Now he's imaging OH. So what we find is there's no combustion until you get down to about 10 diameters downstream, you can see the upper part of the mixing layer and the boundary layer. So all of a sudden you instantly have found out where is it burning. That was pretty impressive. For some reason we got some fuzzy ones here. This was now a cross plane, 15 diameters downstream, and so if you did the fuel image with NO, it looks like here's the region of fuel, but the burning is on the outer edge. Camera was going downhill at this point and the images were getting pretty fuzzy. These cameras have a limited lifetime. Okay, that's all I'm going to talk about. So we're a few minutes, let's see, 2 to 3, 3:15. We're a few minutes ahead of schedule, I guess. Maybe quite a few minutes. Okay, time for questions. So PLIF, harder to do. You got to understand pulse lasers, cameras, electronics. Gives you images that are spatially quantitative, temporally quantitative. Hard to get them quantitative for temperature and species. That's the problem. But potentially it can. So line of sight absorption is quantitative. You have to deal with non-uniformities. It's CW. But you can't say anything about spatial distribution. PLIF, good on spatial distribution, instantaneous in time, good ways to measure a lot of different species, hard to make it quantitative. You have to take your pick. But you can put the TDLAS system in your suitcase or 2 or 3 and go, and you don't put this. You have to use, it's hard to ship this stuff. So, and it's expensive. Okay, how about some questions? Yes?
So, when you're doing the, if you want to know you're saturating, what's the main way you figure this out?
So you typically, if you have some controlled experiment, you typically would kind of repeat the experiment at different laser pulse energy and see if the signal scales linearly with energy. And what you'll find is the signal begins to roll off. So you kind of stay down here where it's linear. But if you have available energy, you keep cranking it up because the signal's going up. So you basically see when it begins to deviate from linear. So in that intermediate plot that I showed you. So in the linear case, signal's proportional to the illumination, the pulse energy. So you just keep cranking it up until you see it rolling off. That's the easiest way to check. So, but you have to have something that's steady enough that you can do that. Yes?
So in PLIF, do you have to worry about any sort of attenuation of your laser beam throughout the flow field?
Yes.
Or is your laser power so high that you don't have to worry about it?
So do you have to worry about the attenuation of the laser beam? So in order to see a signal, you have to have absorption. Therefore, it's absorbing all the way across. So sometimes it's small enough that you can neglect that effect. You can have enough absorbed, but it's still a small fraction of the incident number. So sometimes you're in that regime. Other times you're in a regime where you have to worry about this problem. It just depends. So frequently you'll maybe look and see what's coming out and see how it's been attenuated. So if it's there, you have to worry about it. Then the fluorescence that's emitted has to pass through some absorbing gas. That's reabsorption. That's another problem. So the trouble with fluorescence is that a problem is that in order to get a signal, you need absorption. And therefore, that can attenuate your beam on the way in and on the way out. So those are issues. Sometimes you can model it. Maybe it's negligible. Sometimes you can be clever and you can maybe record how much light's coming out. If it's a symmetrical thing, you can do different tricks. So there are ways of turning that to an advantage so that you can almost become self-calibrating. If you go along a line and you measure by Beer's law, the fractional attenuation, then and if it's halfway symmetrical, you then know what the illumination intensity, so you can kind of work backwards and get this absolute. You at least know from the Beer's law what the absorption was. Then you may still have to struggle with the fluorescence quantum yield. But anyway, those are issues. Good points. Do you have to worry about absorption? Yes. And reabsorption of the fluorescent light. Those are problems. So the bigger the system, the more you have to worry about this problem. Fluorescence works best when it's fairly small. I'm surprised. There should be some more questions. Okay. Here. Oh. Here? Okay.
Yeah, you mentioned briefly velocity.
Oh, okay. Good. So, you know, the Holy Grail in those days, which, and excuse me for kind of recasting history, but I can remember it. Holy Grail was, can you find a way to measure temperature, species, and velocity? So, and there are some strategies. So, for example, in this Doppler velocimetry, if you had, for example, an NO line, and you had a narrow laser, and maybe another narrow laser, you could park them at different places in the side of the line. Or you could maybe have, send one across one way and one across the other, so that when they can't do the two camera images, you look at the same spot, you can relate that the difference in signal to the difference in the line shape, which came about only because of the Doppler shift. So there's some tricks like that. And you can combine different planes, and so yes, it's possible to measure velocity. And so usually you think about this as, well, I need a narrow laser and a broad absorption line. And then I realized that actually you can turn it around. You can have a broad laser and a narrow absorption line and get the same effect. So, but it's always the Doppler effect. It's just a question of orienting beams, and you have to understand either the intensity, the spectral distribution of your laser, or the line shape function of the absorber, and you work on the Doppler effect. So we did that. And some people did it early on, actually a few people did it early on, including Dick Miles at Princeton, where you would scan, say, a CW laser, you'd record the fluorescence, and scan the laser across the line in a steady flow. And your fluorescent signal would look like the line shape. And you can do this from different illumination angles, and you could get, I think I showed an example. I showed an example of, we did this in NO in one of my earlier lectures. But it's always the Doppler effect. So there are ways to do this, either with spectrally narrow lasers or broad lasers. It's just hard, though. And so you have to be, you don't want to do this unless it's your best strategy.
So if signal is proportional to velocity and proportional to concentration, how do you...
You mean volume? That's volume. V was, in those equations, you're asking, was it sensitive to velocity? In those equations I showed, that capital V was volume. Mm-hmm. But there's always somewhere in there a line shape function. So if the laser is narrow, then I got to pay a little attention now to any Doppler effect. So that's a problem, and it's an opportunity.
So the intensity of the line will give you the concentration, while the shift in wavelength of the line will give you the velocity?
Yes.
Okay.
But to do that, you might prefer, maybe if it's steady, it's not a problem. Maybe you scan your laser and you figure this out. If it's not steady, then you have to get clever and use, say, 2 laser beams at the same time. But it's always just, so you don't necessarily want to have to measure the species concentration to take advantage of the line shape. If you can get just the relative shift in the signal, that's enough to give us the velocity. So if your laser, so anyway, there's different strategies. There's no simple one, but it's always the Doppler effect. And that, of course, the higher the velocities, the better it works. So there's some papers in applied optics on this from 20 years ago, 15 years ago. Yes?
When we're talking about quantitative PLIF, then you relate the steady solution, but we also have, when the laser is off, we still have like the tail of the fluorescence. So I guess that you would only record when it's the steady solution, or when you do that?
So that's why what happens during the decay of the fluorescent signal? He's asking. So that's why I showed in the plot the number density going up with time when you have a short pulse of light, and then what happens when the laser light goes off? It dies. What you care about is you want to collect as many photons as you can. You collect all of them. It pulse jumps up and it decays. You collect all of those. It might take 100 nanoseconds. You want all those photons. You want the integral. So, but you could, if you wanted, measure the characteristic time of the decay. Not with a camera, but with a photomultiplier. That contains useful information. That decay time is Q. So there's 2 parts to your comment, I think. Usually when you say, do you have to worry about the decay? No, you don't worry about the decay because you want the total number of photons that are emitted. You want the total number, which depends upon A over Q. But that decay time contains useful information, but you can't get at it with the camera. You get at it with a photomultiplier. So the decay is usually a useful part of the signal. And you wait till that's over before you hit it again. So you don't want to just measure the peak value. You want to get all the photons you can. Your collector just sits there and gathers photons. You want to get as many as you can. So you don't throw this away. But if you really wanted, if you had plenty of photons, you could take a snapshot at different times during the decay and measure Q. That's the strategy, but it's hard to do. You understand? The decay time gives you the information needed to make it quantitative. It's Q. The decay time is 1 over Q. Once you have Q, everything else is determined. But it's not necessarily an enemy, it's an opportunity.
So for atmospheric pressures, this Q, how long is it?
It's the collision frequency here in this room is 10 to the 9th to 10 to the 10th. So therefore it happens fast. I showed in those equations, if you go back and look, the time it takes to get into steady state is kind of 0.1 nanoseconds. The decay time is 1 over Q. It's also fast. But when you go to combustion, sometimes it takes longer. In the thermometry example I just showed you for NO, I remember we took our pictures about every 100 to 200 nanoseconds. So we had to wait 100 nanoseconds before we did it again to get all the photons. But you had to take the picture fast enough that there's no motion. So if you had a low density flow where Q is smaller and a high speed flow, you have to be careful. Because you want to take your pictures fast enough there's no blurring, but if you take them too fast, you may not get enough photons. So you have to always pay attention to Q and your flow speed. And I don't think I answered your question too well, but maybe if you look at my notes, then you can write me. Somehow we went from being late to early. Yes?
I was just wondering, do you think that PLIF will ever be something that's sort of like routine and easy and inexpensive? Is there any
Those are different questions there. Will it ever be canned and easy and inexpensive? I think it can be. Yes, it could be. So if you could, well, we try to use a simple laser. I didn't show, in the next hour, I'm going to show you some results where we tried to do this. We tried to use a simple laser. It was still expensive. It was maybe $50,000. We tried to use a simple laser, no knobs, no wavelength tuning. We tried to use a simple camera, no knobs, unintensified, and a simple experiment where Q is a constant. And it's pretty portable. It could be. Now, could I put it in a suitcase? Probably not. Unless your experiment was kind of small, that is, if you're looking at something small, you might be able to get away with some lower energies. I can imagine some situations where you could do this, but it's not going to be in an engine or in a big experiment. It's still pretty pricey. PLIF is much more expensive than laser absorption. But for a small enough experiment, and if you just wanted to study mixing maybe, it could be. These cameras are nothing more kind of like a digital camera. Scientific quality, digital camera is all it is. You know. So cameras have become a lot cheaper. So if you can do an experiment where you do not need to use an intensifier, it could be, the camera could be cheap. Now if you can use an experiment where the signal's kind of big, you don't need a big laser, just a simple laser, it could be, you know, I can imagine a system that costs maybe $20,000, possibly.
I guess one of the things I was wondering is like, if you weren't making that restriction about being, for experiments that are like well suited towards this inexpensive version of this, do you think there's ever going to be a time when PLIF could be refined to the point that it becomes a very common sort of diagnostic that we're using all over the place, even for stuff that's presently very, very prohibitive?
So the question is, will it, could it be so, I guess, user-friendly that it would be widely accepted? User-friendly and economical. Yeah. Well, the problems are it's still fairly sophisticated and it's still real expensive. So, but still, you go around, I bet you could find a dozen or more systems in China, maybe hundreds of systems around the world, but they're mostly used in research laboratories. But some of them now are practically turnkey. Maybe the person is a master's student, maybe not necessarily a PhD. So if you're just going to do something fairly routine, I can imagine somebody doing this that doesn't have to know any spectroscopy. And you'll see that in my next, I think my next lecture is kind of addressed to the sort of thing you're asking. The attempt is to make it user-friendly, to make it versatile, to get it, I called it dumbed down, to get it for the fluid mechanics people. Or heat transfer people, or, you know. Well, I think we're almost exactly on time. Oh, one more question?
I'm just curious if you have strong gradients in density that cause beam steering, and also you're just locally changing the concentration because the total pressure and all of them are coupled. So I'm just curious, which of those is the most pressing problem, I guess, or are they all sort of on the same order?
Well, okay, what about, you said beam steering or perturbation of the flow, I guess would be the two questions that you might worry about. Beam steering is a density gradient problem. It's actually index refraction gradient. So the longer the path, the higher the pressure, the steeper the gradients, the more the beam steering. For PLIF, that isn't such a big problem because it's a linear process. It's not requiring that we mix two beams and maintain some alignment. As long as your depth of field is such that you can still kind of capture that image, I think beam steering is not a big problem, but it becomes a bigger problem when the pressure goes up. We ran into this a little bit at 50 atmospheres. But it's pressure, path length, but you have to have some depth of field to your collection so that you don't. Now it may also cause the beam to get a little bit broader so that your spatial resolution in the transverse direction is not so good. So we've never been stuck with beam steering. The other question is, do you actually perturb the flow? Well, these are usually flows, not a static system. For a static system, not moving, you know, you're adding energy to the system. If you have an absorbed photon, the success rate is A over Q. And if A over Q is 10 to the minus 3, it takes 1,000 absorbed photons to give you 1, and then you only collect 1% of those. So so that most of you're not collecting much of the light. Where's the rest of the energy? Where's the 999 out of the 1,000? It goes into heating. So if you just sit there, you're transferring energy to this container. But usually it's not static like this. It's usually flowing, and if you're in the linear excitation limit, you're not really removing that many molecules. So that's not usually a problem either. If you put in enough energy, you can start to get in this intermediate nonlinear regime. You got to be careful about that. That's the intermediate result. So usually you don't run into trouble with perturbing the system, especially if it's a flowing system. So there's a subtle distinction now between in situ and non-intrusive or non-perturbative. It can be in situ in the sense that you're measuring it in place, but if you send in enough photons, it's perturbing. So we have to kind of be careful about our words. We would say that this is in situ, and usually we'd say non-invasive. Sometimes maybe someone would say non-perturbing, meaning that you're not changing anything significantly. That's the goal, but you could certainly, well, some people study, I studied with Jerry Seisman, we studied laser ignition. You send in light with the purpose of causing a problem, and then see what would happen. So you can certainly do that. If you focus the light, well, you'll also see, if you focus the light too much when you go through your window, you're going to burn the window. Then if you focus it inside the gas, you may cause it to create a spark. So these pulse lasers are now intense enough that you can cause those kind of changes. But it's not really a beam steering problem or perturbing the population unless you intentionally want to cause a plasma breakdown. In that case, you might use one laser to cause, well, what we did is we used one laser to create a spark, and then we did PLIF to watch the propagation. The last one didn't really perturb the flow, the first one did. That would be like laser ignition. Anything else? So I think we're exactly on schedule. If we resume at 4:30, we'll be done at 5:30. Time to go to the reception. Okay?